This is part 5 in a series of videos in which I am demonstrating how to use a logic analyzer to develop a system. And this is just for the basics of using a logic analyzer. If you're familiar with them, then you probably won't find these videos of much interest. But as part of this series, what I decided to do was set up a simple demonstration system, and I would use this as part of the process of developing the use of the logic analyzer. Now, this system is based around the Signetics 8X300 microprocessor, and this is a particularly interesting device. It's the precursor to the modern PIC microcontroller. The actual processor itself is really the core, and there are various support chips that I will also be using as we go through this series. And the reason I chose this is, firstly, it's a very interesting processor, but also it gives us access to effectively the inner workings of a microcontroller that we wouldn't normally have access to. You don't normally have access to the internal buses, you only have access to the external ports, but with a setup like this we can gain direct access to those internal signals, and it makes it easier to explain how it works, but also will be far more interesting in using the logic analyzer. To make this easier, I've kind of branched off for a little while, which is why it's been a while since the previous video in this series, and that was to develop an assembler for this device. I've now done that, and if you haven't seen the series of videos on developing the assembler, you might want to see those. But now I have an assembler, so I can take basic instructions and compile them or assemble them into code that can be put into the ROM. And I demonstrated that in the last video in the series on the 8X300 assembler. So what I did then is use the assembler to create some very simple code for the system. This is the code that I developed, very simple. It's a label or two labels and two jumps. So the first instruction jumps to the second label, and then the instruction there jumps back to the first label. And because these are the only two instructions in the program, all that will happen if this runs is it will jump back and forth between address 0 and address 1, and that's what we should see when we start examining this in more detail. But if we look at this on the scope, so what I have here is the system set up with that code in the ROM. I've only got the first three address lines hooked up at the moment. All the data lines are of course hooked up, but I only need the first three address lines at this point. We've got the reset line as well, just in case I need to reset it. Talking of resets, there will be a repair video coming up sometime soon. I've got an issue that's developed with my Rigel DP832. In fact, it's been an issue since I first bought it. It's quite an expensive linear supply, but it's got a habit of resetting itself, and it used to do it once every hour or so. It now does it every 2 or 3 minutes. It's extremely annoying, but I need to get that repaired. So if I keep stopping halfway through a test, is to reset that supply. I think it's something Rigel need to get sorted out. Okay, so back to this, and I'll re-enter the settings in the supply and power this up, and I've got the scope set to look at the master clock output from the processor and one of the data lines, so we should see the data for that bit toggling as the system jumps back and forth between the two addresses. So we'll power this up. Reset it. And so, as you can see, it is running quite nicely. The yellow signal is the clock, and the blue signal is the one of the bits for the data bus. So what we'll do now is we'll hook up the logic analyzer and see how we can start using that to analyze a system like this. Okay, I've got the logic analyzer hooked up to the basic signals. Pod 1 is hooked up to the data bus, and pod 2 is hooked up to the address lines. As I said, I'm only currently using 3 address lines. We'll add more as we need them. And so what we'll do now is I'll move the camera so we can see the logic analyzer, and we'll get that set up to look at these basic signals. Okay, so looking at the screen of the logic analyzer, as usual I've created a directory to hold the configuration, so we'll select that first. And now we can select the configuration itself. Okay, and the initial configuration I've got set up for this is fairly straightforward. So we can see that we have the data bus is set on to pod 1, all 16 bits, and the 3 address lines are on pod number 2. And this is a basic trigger. All we're doing here is setting on what I know will be one of the values we're going to see on the data bus. If you don't know what values, then just get it to free run to start with, but as I say, I know that this is what we'll see because that's what we saw in the assembler when we assembled the code. So if you recall, this is what we have in the program. So we're just going to jump between 2 addresses, and the data that we should see should toggle between E000 and E001, which is a jump between those 2 addresses. Let's reset the supply yet again, and we'll power that up. So I've now got the signals present on the scope as we saw a few minutes ago. We'll now look at the waveform and we'll run the analyzer. Okay, and as you can see, we are indeed getting the values that we expected. The clock is being obtained from the master clock on the processor, and as you can see, the data bus is indeed toggling between the 2 expected values, and the address bus is toggling between 0 and 1, which again is exactly what we would expect it to do. So it is running this code successfully. There's not a great deal else we can do at this point. Now, one thing I would point out is that because of the way this particular processor works, and in fact any processor that has multiple clocks for each instruction, you do need to be careful where you obtain the clock. So there are 4 clock transitions for each instruction in this processor, but that's not 4 transitions of this clock. This only has 1 cycle per instruction. So if you wanted to look at more information, which we will need to do later, is we'll have to obtain the clock from a different source, and we'll have to get it directly from the X1 input to the processor. But I'll come back to that later when we need to start doing that. For now, what we'll do is we'll look back at the development board and see how next to progress with it, and what we're going to do to use the analyzer as we go through this development. Okay, so looking back at the development system, the next thing we want to do is start making more use of the analyzer and to start to expand the development of this hardware setup. So I'll just power this off. I'll remove the clip from the ROM, so I've got this clipped onto the ROM, of course. And what we want to do now is start adding some additional hardware to this. So the next thing, next obvious choice is to add some ports. If we look at a page from the datasheet for the ATEX300, then this is showing a very simple generic type of system. And at the moment what we have is effectively this portion on the left. So we've got the controller itself, we've got the regulator circuit, which is what the transistor was that I mentioned in a previous video. And we've got a single ROM here rather than 2, so that is of course this. And what we want to do now is start adding these ports, or at least 1 or more ports, so we can start doing something a bit more interesting with it. And then later on we'll add some RAM as well. Now this processor, again, this is one of the reasons I chose this processor for this particular project, because it is quite interesting. So one of the first things to note, I don't know if you can actually see this, but it's saying address lines here A0 to A3 are not connected in this configuration, but lines A4 to A12 are. And it might seem a bit odd why we are starting with what appears to be the non-least significant bit for the address. And this is something you'll come across a lot with old documents and old data sheets, and it's something to always bear in mind that although you may have become used to certain terminology and certain ways that things are done these days, it never used to be, or wasn't always the case. It did vary quite a lot. Recent video, somebody mentioned that I put a key in the wrong place when I was restoring the ASR33, but it wasn't in the wrong place. It's just that key definitions used to be somewhat different. And the same is true here, whereas these days we're normally used to A0 as being the least significant bit. In this particular data sheet, A12 is the least significant bit and A0 is the most significant bit. So it's actually the most significant 4 bits here that are not connected, not the least significant. And the same is true with the data as well. So when you're hooking this up, you just need to bear in mind that although it's showing the data lines as being from 0 to 15, bit 15 in the data sheet is actually the least significant bit. And that's something, of course, you need to take into account when connecting it to the ROM. Next thing we want to do though is hook up one of the in-out ports. Now the friend that sent this to me was generous enough to also send some of the in-out ports, and these are quite interesting devices themselves. Let's grab the data sheet, or at least part of the data sheet for one, and they are quite interesting. It's really just a latch, a bidirectional latch. However, there is a complication when using these, or simplification depending on how you look at it. So these are not connected to the data bus as they would be in a normal system, or the address bus as they would be in a normal system. This device is a bit like an unraveled Z80. You're probably familiar with the Z80, and it has specific in-out instructions. Well, this processor does as well, except it doesn't share the buses, or at least it does multiplex one of the buses, but it doesn't share them between ROM and the in-out system. So if you notice here, all the ports are connected to a common bus. It's an 8-bit bus, and the question there, of course, is, well, how does the system know how to address each of these ports? Because if they're all connected to the same one and there is no logic to select them, there's no separate logic to control them, all the chip enable lines are common, how does the system know which of the ports it's writing to? And the answer there is easiest to explain if we look at the devices themselves. Now I don't know if you'll be able to see this or not, but you've got the device here. These are incidentally N8T32Ns. As I said, they're bidirectional latches. So you've got the part number at the top, but also you've got this number down here. This first one says 001, this one says 002, 003, and 004. And this one is much bigger. When you ordered these, you had to specify what address you wanted. And what this does, it enables the system to differentiate between different devices. So what you would do is you would order different address numbers, and the way that this processor accesses the latches is a 2-step process. First, and this is an 8-bit bus, the first 8 bits are an address. It sets that address up, and it effectively forewarns whichever port has a matching address that it's about to send or request data from it. And then the second phase of the interaction is to either send data to the port or to request data from the port. and the one that responds is the one that was previously set up in the addressing phase. And so, for example, what we have is 001, 002, 3 and 4. So that's how we would go about deciding how to access each particular port. So what I need to do is get these hooked up. There's a few control lines, but as I say, it's mostly hooking up the address and data lines. As I said, these are the address and data lines on the same bus, not to be confused with the address and data lines for the ROM. So I'll get that done, I'll get back on camera and see if we can get this to actually do anything. Before it will access these, of course, we will have to go back to the assembler and write some more code. Okay, so looking back at the assembler, we'll enter program test B, and this is just going to be sending a value repeatedly out to the port that will be connecting to the processor. So again, we'll start with a comment. Okay, so the first thing we want is a label, so we can jump back to the start of the program. It'll just be looping round indefinitely. So we'll call that loop 1. And then we want the first instructions. So we'll use the XMIT instruction because that will allow us to enter a value directly. We won't need to load a register first. It'll be the simplest approach to this program. So the form will be XMIT and then the port number that we want to use. So this is the address ID number of the port chip. Now I've selected port chip 001, so we want to address that. So the first XMIT will be setting up the address on the IVL bus, and I've also got the device hooked up to the left bank of the processor, so we need to use IVL, and then of course we have to tell it what to actually send. So we want to send a value, again using XMIT. Just for the test we'll send, for example, 03, and then where to send it to and how many bits to actually send. So again, just an arbitrary value. If you're doing a real system, you would of course need to make sure you're sending the right number of bits and rotating them correctly, etc. So that sets up the address. We now need to send some, that's set the address and the actual data we want to send, and then to make it toggle rather than just setting something and it staying the same so we can see if it's actually active, we want to send a different value. We want to send it to the same address, so we'll repeat the first setup instruction. So we'll set up the same device and then a different value to send so that we can see hopefully the bit toggling. So in this case, again, an arbitrary value of 4 to the same place, and again we'll put an arbitrary number in there as well. And then finally we just want to jump back to the start of the program, so we'll just use a simple jump back to loop 1. So what we've done now is set it up so that we've got the first instruction will set the correct address for the device that we have. That's the hardware address for that device, and then the value we want to send, we then replace that value to the same device with a different value, and that's the entire program. So we'll assemble that. Okay, no errors, and this is the resulting code. So we'll open up the programmer, load the file, so in this case it's test B, and we'll just check to see that we've got what we expect, and it looks right. The last command is of course to jump back to 0, and what we can do now is insert a device into the programmer. You can't see that, I'm just popping a ROM into the programmer. Hit program, Wait for that to complete. Okay, and then we'll take that device over to the board and see if it actually works. So as you can see, I've got one of the port chips installed. Although we only need to toggle one bit, I have to connect up the entire 8-bit data value because, as I said, that is also the address bus in the first phase of sending a value or retrieving a value from the port chip. Again, don't know if this chip works yet, but I've got it hooked up what I think is correct, and what we can do now is insert our new program. I'll need to move the scope so we can monitor one of the outputs of the device. So it was bit 5 that we should be toggling, which should be that one. And it all looks correct. And so if we power this up now, again the yellow trace is the master clock, and the blue trace, we should see it toggling every few clock cycles as we write the alternating values to the port. So I'll power up the board, and indeed we can see that it's working. You can see the blue trace is cycling up and down as we would expect, and this is in response to us writing the value of 3 followed by 4 followed by 3, etc. to the port. So that's now working, and in the next video what we'll do is we'll hook up the logic analyzer to the in-out port chip, and we'll see how the signals look on that particular device, and also why we will need to select a different clock if we want to look at the interaction in more detail.